Hello, hello. Let's jump into section 4.2, eigenstuff. Eigenstuff is eigenvectors, eigenvalues, but they go together so much, I just like to call them eigenstuff. So let's read this definition. This is going to be closely related to what we did in 4.1. And in 4.1, that was kind of a bigger section because we actually got a lot of the work out of the way. Like, we figured out why multiplying by powers of matrices is useful in applications when we have difference equations where we have like sequences of vectors like this. And we saw how it was useful to diagonalize the A matrix. And we're going to apply what we learned there to this concept of eigenvectors and eigenvalues and explore the concept a little bit more here. So if you have a square matrix, a C by C matrix, we say that X is an eigenvector corresponding with an eigenvalue, lambda, which is a scalar, of A, if multiplying A by X is equal to that scalar multiple, lambda times X. And X has to be not 0. So we already had an example of this right here. This is saying that V from this exercise 1 warm-up was an eigenvector of A corresponding with an eigenvalue, lambda equals -2. And X is not an eigenvector because doing A times X does not give you a scalar multiple of X. Okay, so that's the idea. Let's look at some examples. Now, we do want to keep in mind that lambda times X being a scalar multiple of X means that it's on the same line through the origin and X. And you can see why maybe X is not equal to 0 should be required here, because if 0 could be an eigenvector, then like A times 0 is always equal to any scalar multiple of 0 that you want. So we would be able to say that 0 is an eigenvector that corresponds with every single real number eigenvalue. And that's kind of like this trivial solution, sort of weird edge case thing. We're not going to call that an eigenvector. So only non-zero vectors can be eigenvectors. So let's look at an example. Here is this matrix A. Explain why A has no real eigenvalues. Now, does this look familiar? Have we seen a matrix like this before? These fractions at least look like some common trig function values, right? Yeah, so this is actually a rotation matrix where we have cosine of 60 degrees, sine of 60 degrees as the first column, and then negative sine 60 degrees and cosine 60 degrees as the second column. And that means A is a 60-degree rotation matrix. So if E1 is right here, then A times E1 is about right here, and E2 is here, and A times E2 has been rotated also by 60 degrees. Now, any X anywhere, if you rotate it by 60 degrees, is no longer going to be on the line through X and the origin. Like maybe you have an X that is over here somewhere. Scalar multiples of X would have to be somewhere on this line. But a times x is going to be 60 degrees over this way. And that's true for every point except the origin. And the origin is not allowed to be an eigenvector. So this has no eigenvalues because you can't have an eigenvalue unless there's an eigenvector that goes with it. Okay, so yeah, if there's no eigenvectors, then there's no eigenvalues to go with those eigenvectors. So there's no eigenstuff in general. So this is an example of a matrix that has no eigenvalues or eigenvectors. Let's actually look back at something in 4.1 really quick from back in the day. Here we have example 4 where there was this matrix A, and we found with this matrix that there were some vectors, like this purple version of x0 right here, where x1 is equal to 2 times x0, right? Remember, the definition of x1 was a times x0. So we have a x0 equals 2x0 here. So that was a multiple of b1. And also b2, with this x0, if you do a times that x0, you get 1/2 x0. So this x0 is an eigenvector of A corresponding with eigenvalue 1/2. This purple x0 over here is an eigenvector of A corresponding with eigenvalue 2. And let's see here, this x0 in green over here, when you multiply that by A, this x1 is not a multiple, it's not a scalar multiple of x0. It's not on the same line through the origin as x0. So this is not an eigenvector of this matrix A, but the purple x0 over here was, because x1, which is A times x0, is half of x0. And also, if you have multiples of b1 with this example, multiplying them by A doesn't change them at all. Like with this orange one here, any power of A multiplied by it doesn't change it. So A times this orange x0 is just 1 times x0. So that's an eigenvector that corresponds with eigenvalue 1. Here's an example 6, where you have an eigenvalue of 0. The purple x0 here, if you do A times that purple one, you get the origin. So in other words, A times x0 is equal to 0x0, the origin. So that means 0 is an eigenvalue of this. And maybe you notice that 0 is this diagonal entry of this matrix. And also 1 is a diagonal entry of the matrix. And when you do A times this orange x0, you just get 1 times x0. It doesn't change it. That's not a coincidence. And we're going to see why this is in the next video. That's what the diagonalization theorem is about. That was kind of a preview of that. Example 2 is also sort of going to justify that theorem as well. So we'll go over that next. See you then.